Hi everyone. In this video, we are going to explore selection sort algorithm. We'll go through an example, discuss its efficiency, and even write a code to implement it. To start, we will use ascending order for sorting. Let's get started. Selection sort is a simple sorting algorithm that works by selecting the smallest element from the unsorted part of the list and swapping it with the first unsorted element. This process continues until the entire list is sorted. Let's start with an illustration. Given an unsorted array of length 5, it is easy to see that 6 is the smallest element, so it should come first, followed by 7, and so on. But how do we achieve this programmatically? Using idea behind the selection sort. That is, select the smallest element from the unsorted part of the list and then swap it with the first unsorted element. We start with the first pass. Here, entire list is unsorted, and we assume that element at index 0, that is 8, is the smallest and perform the successive comparisons. 8 is first compared with 9, wherein we check if 8 is less than or equal to 9. 8 is smaller. 8 is then compared with 8 present at index 2. 8 is less than or equal to 8. Here the 8 which is at index 0 is equal to 8. So 8 which is at index 0 will retain its position as the smallest element. 8 is then compared with 7 present at index 3. Here 8 loses its title to 7. Now 7 is the smallest element. 7 is then compared with 6. 6 is now the smallest element, and we have reached the end of the list for pass 1. And the 6, since it is the smallest, it needs to be swapped with 8. So at the end of pass 1, the smallest element 6 has reached to its correct position. Now we start with the second pass. In the second pass, the unsorted list starts from index 1. We assume that element at index 1, that is 9, is the smallest element. 9 is first compared with 8. Here 8 is the smaller, so 8 becomes the new smallest element. 8 is then compared with 7. 7 emerges to be the smallest element. Then 7 is compared with 8, which is present at index 4. Here 7 is still the smallest element. So since we are at the end of the list and 7 is the only smallest element, 7 is swapped with 9. So 7 will occupy the position of 9 and 9 will come at the place of 7. So at the end of pass 2, we got two smallest element from the list. Now let's start with the third pass. Here the unsorted list starts from index 2. We first compare 8, which is present in index 2, with 9. We check if 8 is less than or equal to 9. Since 8 is less than 9, 8 will be the smallest element. Then we check if 8, which is at index 2, is less than or equal to 8, which is at index 4. Here 8 is equal to 8. So 8 from index 2 will retain its title as the smallest element. Here there is no need of swapping because 8 is already in its correct position. So at the end of pass 3, we got 3 smallest element. Now let's start with the fourth pass. We assume that 9 present at index 3 is the smallest element. 9 is compared with 8. Since 9 is greater than 8, 8 becomes the smallest element. And since we are at the end of the list, 8 emerges as the smallest of the two, and 8 will take the position of 9 and 9 will come at the place of 8. And now the list is finally sorted. Now let's evaluate the performance of selection sort. With 5 elements, the number of passes is 4. And for n elements, the number of passes can be generalized as n minus 1. Total number of comparisons. If we observe, pass 4 had 1 comparison, pass 3 had 2 comparisons, pass 2 had 3 comparisons, and pass 1 had 4 comparisons. So in total, we performed 10 comparisons. For n elements, this can be generalized as 1 plus 2 plus 3 plus n minus 1, which is equal to n minus 1 by 2, and this can be simplified as big of n square. In selection sort, only one swap is performed per pass. With 4 passes, ideally there should have been 4 swap, but in this example, pass 3 did not result in any swap because 8 at index 2 was already at its correct position. That's the reason we are getting the total number of swaps as 3. But if you generalize it for n elements, then the total number of swaps will be big O of n minus 1, which is equivalent to big O of n. The time complexity for selection sort is big O of n square for all the 3 cases. And the space complexity is big O of 1, constant, because the swapping is done in place. Selection sort is a non-stable algorithm, meaning the relative positioning between elements of the same value is not guaranteed after the sorting. If you notice, in the original array, 8 in red was coming before 8 in black. But after sorting, a final result, if you see, 8 in red is appearing after 8 in black. So, selection sort is a non-stable algorithm. Let's now implement selection sort. First, we need to find the length of the given array. Then, we need a loop to carry out n minus 1 passes, a variable to keep track of the smallest element in the unsorted part of the list. Then, we need an inner loop to carry out comparisons. This inner loop will update the index variable if any smaller element is found. After all comparisons, the first element from the unsorted part of the list will be swapped with the smallest element found. These steps will be repeated for n minus 1 passes, eventually sorting the list. Here are the steps for your reference. Feel free to revisit the visualization section if needed. Thanks for watching.